Hello everyone, I'm Yingning. I'm going to present our work, Effect Handlers in Haskell, Evidently. It is now well known that the standard way to incorporate computational effects to the world of functional programming is by using monads. Monads, in general, do not compose. We thus need monad transformers. However, for monad transformers, it is necessary to explicitly lift operations through the transformer stack. Implicit lifting is possible but restricted. On the other hand, algebraic effects and handlers provide a useful way to encode composable and modular computational effects. Recently, several work have shown that algebraic effects provide an alternative to monads to incorporate effectful programs in Haskell. In particular, effect handlers can express any free monad in a concise and composable way, and can be used to express complex control flow like exceptions, asynchronous I/O, backchecking, and much more. In this paper, we present a new Haskell library for algebraic effects and handlers. We argue that our library interface is remarkably concise and simple. In particular, in our recent ICFP work, we show that polymorphic algebraic effects can elaborate by an evidence passing translation to a polymorphic evidence calculus, which can then elaborate by a monadic multi-prompt translation to polymorphic lambda calculus. Besides giving precise semantics, this translation also allows for potentially more efficient implementations. Here, we present the first implementation of this technique as a library for effect handlers in Haskell, named control.ev.f. In this implementation, we combine the two translations and thus go directly from polymorphic algebraic effects to polymorphic lambda calculus. Specifically, our library has the following structure. The library provides an interface for algebraic effects. Underlying the interface, algebraic effects elaborate by evidence passing to a multi-prompt monad. In the rest of the talk, we first go through the library interface, and then take a closer look at the implementation details, including optimizations for tail resumptive operations and the restriction called scoped resumptions. Finally, we give detailed benchmark results and show that the performance of the library is quite good by comparing its performance with the monad transformer library and other Haskell libraries. To understand the library interface, let's start with an in-depth example of dynamic binding, also known as the reader effect. Using our library to define a new algebraic effect is straightforward. We simply declare a new data type. The data declaration defines a new effect reader with three type parameters: A for the reader value, and E and S for the effect context and answer type where the reader is handled. Its constructor reader has a single operation field ask, with type op unit A, E, S, which denotes operations from type unit to A in an effect context E with answer type S. To perform operations, we pass the operation ask with its argument unit to the perform function. Effectful computations run in the F monad, where E is the effect context and string is the result type. The type class constraint reader string column $E, which we pronounce as reader string in E, indicates that the effect handler reader string is a member of the effect context E and can thus be used to perform operations. In this case, perform ask unit returns a value S of type string. Operations are given semantics by their handlers. We can handle a reader effect in an action using the handler function. The first argument to handler is a concrete instance of the reader data type with an implementation of the ask operation. In this case, we use value to always resume with a constant value word when ask is performed. The value function is just one way to define operations, but there are various other ways which we discuss later. The reader action has effect context reader string cons E, where the type constructor column star, pronounced as cons, represents the effect context as a type-level list, which has effect reader string as the head and the effect context E as the tail. We can view handler as an elimination rule where the reader string effect is eliminated from the effect context. Since action has reader in the effect context, it can perform operations in the reader effect. In particular, we can evaluate greet under our reader handler, where the constraint is satisfied. Now, since ask is handled by returning word, we expect greet to return hello world. We can run effectful computations using runf, and it returns the result as expected. Note that this slide is all that it takes us to write a complete algebraic effect program. To allow for more complicated examples, as we have mentioned, there are various ways to define operations. First, we have seen value in the reader example. This is used to create operations that always resume with a constant value. In practice, most effects can be defined using function. It takes a function from the operation argument A to the operation result B in the effect context E. We can define the ask operation of the reader in terms of function as well. Finally, operation is the most general way to create an operation. It takes a function that expects two arguments, the operation argument A and a resumption, which takes the operation result B and returns the answer type S in the effect context E. One can explicitly call the resumption to resume to the original call set. This is the essence of the algebraic effects. The resumption can also be resumed multiple times to implement things like backchecking. If the resumption is never invoked, the operation behaves like an exception. We refer to our paper for more examples, including an implementation of a parser combinator. Now let's dive into the implementation details. As we have shown before, algebraic effects in our library are built upon evidence passing to a multi-prompt monad. This involves two monads. First, the algebraic effect monad, as we have seen, is the F data type. The multi-prompt monad, as we will introduce later, is implemented by the control data type. Then, what exactly is the evidence passing? It turns out that the definition of F is, instead of a data type, a new type declaration. That is, F is isomorphic to the function type from context to control. And this context represents exactly the process of evidence passing, where a vector of handlers is passed down as the context. To understand how evidence passing works, let's consider this program. This code has three handlers, followed by an expression which simply calls ask twice and returns the sum. The three handlers are a reader handler, which resumes the computation with 1, an inc handler, which increases the computation result by 1, and an exception handler, which returns a default value 3 if the computation fails. Since the reader always returns 1, we expect both x1 and x2 to be 1, and thus the answer to be 2. Now, let's look at how this expression evaluates. We first evaluate the reader handler. Here, we create a fresh unique marker represented as M1 to denote this particular reader handler. We call the pair of the marker and the handler an evidence. And we pass the evidence down as we evaluate. We then evaluate the inc handler by creating another fresh unique marker M2 and pass the new evidence along with the existing reader evidence. That is, we now have an evidence vector, which is exactly what the data type context denotes. We keep evaluating the exception handler and get one more evidence. Now we hit the ask operation, and we inspect the evidence vector. From the evidence vector, we find that the reader handler that is supposed to handle this operation has marker M1. We can then yield up to find the handler marked by M1. We check the exception and the inc handler until we reach the correct reader handler. which says that we should resume with integer 1. Now we resume and go back to where the operation is handled. For the second ask, we repeat the whole process again. This part of yielding up and resuming is exactly what the multi-prompt monad control does. With the evidence passing semantics in mind, now let's look at the implementation of the control data type and the context, respectively. The control monad implements the semantics of multi-prompt delimited continuations. The pure case has a value result, and the yield case reflects yielding to a prompt. Yield stores three components: a unique marker indicating the particular prompt to which it yields, an operation implementation op that is already partially applied to its operation argument, so it just needs a resumption to evaluate its action, and the partially built-up continuation count. Since count is partially built, its result type A can be different from the final answer type nth. Once the right prompt is reached, the markers will ensure that at that point A will be equal to nth. Now we proceed with the implementation of the evidence vector, or the context. We have seen this particular evidence vector with three evidence. Now, what type can we give to this evidence vector? Ideally, we may want to say that it is a list of pairs of the marker and some handler type. However, inspecting the type of each element, we get that the first evidence is a pair of the marker and an exception handler. The second is a pair of a marker and an ink handler, and the third is a pair of a marker and a reader handler. Moreover, users can easily define more effects and thus get more different handler types. That means there is no such a unified handler type. Instead, the effect context is a heterogeneous list. We thus represent the context using a GADT. The CNEO constructor is an empty context, while CCons takes the marker, a handler, and the tail of the context. The type constructor column star, which we pronounce as cons, is a phantom data type and has no runtime representation. Using the GADT representation, the evidence vector is represented as a sequence of the exception, followed by a sequence of ink, another sequence of reader, and finally the CNEO. We can write down its type as the context of the three handlers. Now we have the representation of the context. There is one more question left. That is, to perform an operation, we need to be able to select the correct handler from the effect context. The type class constraint h in E exposes the subcontext function to do exactly that, where the data type subcontext simply returns the correct handler h, along with all the handlers after it in the context. We still need to define the instances for subcontext. In principle, we would like to simply define two instances. One, where the head of the context matches the handler type. In this case, we simply return the context. And one where we need to recurse into the tail. Unfortunately, this does not quite work. If we load the definition into GHC, we get an overlapping instances error. That is, as we cannot directly express the type inequality between h and h prime, these two instances overlap. This is a known question in Haskell, and many solutions have emerged over the years. In our work, we choose to encode type-level equality using type families. In particular, there are three steps to define the type class h in E. First, we define a type-level equality function using type family h equal, which returns true if two handlers are the same, and false if they are not. Here, the true and false are values promoted to the type level by data type promotion. We then define another effect constraint in eq. The type signature of its function, subcontext eq, is exactly the same as subcontext, which selects the correct handler h1 from the effect context h2 cons E. What makes inEq special is that its type parameter heq records a result of whether h1 and h2 are equivalent. In the final step, we define the instance of h_in_e by simply using inEq and calling subcontext eq. But we are not done yet, as we haven't defined the instance of inEq. Like before, we have two cases to discuss, with the two same definitions. But unlike before, now we can discuss explicitly whether h1 and h2 are equivalent. In particular, when h equal h1, h2 is true, we can simply add it to the constraint. But this is the same as saying h1 and h2 are equivalent. When h1 and h2 are inequivalent, we add it to the constraint. Also, since we recurse on the tail, we also add the constraint that h1 is in the tail of the context. With that, we are done encoding that h is in E. We refer to our paper for more details about the implementation. Now, let's move to the optimization and revisit the previous example. Before, during evaluation, we get the handler marker from the evidence vector and yield up finding the handler using the marker. But in this case, the evaluation can be faster. That is, for this example, we don't need to yield up at all. Because from the evidence vector, we do not only know the marker of a handler, but we also have the handler itself available. From the handler implementation, we know that the reader handler has a tail resumptive implementation. Therefore, we can evaluate the handler in place and get a result 1 as the result of ask. We can then directly continue the evaluation. We then hit the second ask and get another one. Compared to the previous evaluation, this time the evaluation is a straight line, which means that it does not change the control flow at all. This is thus much more efficient than the previous one. In summary, with evidence passing, tail resumptive operations can evaluate in place. Non-tail resumptive operations still need to yield up. But from the evidence vector, we can locally decide which marker to yield to, which is more efficient than finding the right handler dynamically. However, our evidence passing semantics comes with a restriction, that is, scoped resumptions. The notion of scoped resumptions is a restriction of general effect handlers where resumptions can only be applied in the very scope of their original handler context. This is crucial for the evidence passing semantics to be sound and coherent. However, we believe all important effect handlers can be written with scoped resumptions, including complicated examples like async or concurrent scheduling. In this work, we follow our SFP work and use a dynamic check for scoped resumptions called guard. We refer to our paper and also our SFP work for more details regarding scoped resumptions. Finally, having discussed briefly about the efficiency of the implementation, let's talk about benchmarks. We show that the performance of our library is quite good. We compare the performance of our library EV relative to the latest extensible effects library EE, the latest fused effects library FE, and the monad transformer library MTL. We also have an EV-NT version where all handlers are always defined in a non-tail resumptive way, and thus lose the optimization for tail resumptive operations. Our benchmarks are taken from the extensible effects paper. As a basic check, we use the counter benchmark, which recursively counts down using a state effect. With 10 to 7 as the initial value for the state, the result is given in this table. The pure, MTL, and FE versions are all quite fast, where the pure version is simply a tight loop for counting down. Here we can see that the state monad is highly optimized in GHC, and FE has special build rules triggered. Our EV implementation is about 5.5 times slower than those. However, as it uses internally an stref, and it performs very close to a plain runst implementation. It is close to optimal, and only limited by the performance of runst in GHC. EV is respectively 7 and 18 times faster than EE and EVMT. Comparing EV to EVMT, we can see that evaluating their resumptive operations in place is really effective. The counter benchmark is a bit unrealistic, as it can be heavily optimized as a special case. We thus also use another benchmark from the extensive effects paper, which is a variant that is perhaps more indicative of performance in real programs. Here, the program falls over n numbers to find its maximum, and performs a get and put whenever it hits a multiple of 5. That is, instead of a pure loop, in every iteration there is some calculation. This time, the pure version models state as a tuple. We use 10 to 6 as the value of n, and the result is given in this table. Now, the performance of all library is more aligned. Our library EV performs best here, and is about 1.5 times faster than the next contender EE and FE, which perform similarly. We use the realistic state counter to further evaluate performance when there are multiple layers of effects. This is also closer to real-world programs, where there are usually combinations of multiple effects. In this benchmark, we put many reader layers under or over the target state layer. In the left figure, we put the state layer at the bottom of the layer stack. As we increase the number of the reader layer over the state layer, our EV runs in constant time, EVNT runs slightly slower, EE and FE runs in linear time, and MTL seems to run in quadratic time. On the other hand, if we put the state layer at the top of the layer stack, that is, in the right figure, as we increase the number of the reader layers under the state layer, EV still runs in constant time. This time, EE also runs in constant time, while EVMT, FE, and MTL seems to run in linear time. For this benchmark, again EV is faster than the other alternatives. Notably, there is little extra cost to adding more reader layers over or under the target state layer. We believe this is due to those operations being tail-resumptive, and thus they are always evaluated in place and never need to yield up. In summary, we showed that our library has good performance, and when combining multiple effects, our library tends to outperform monads and alternative effect libraries. Please read our paper for more details. In particular, we have provided utilities for more advanced handlers, including handlers with return clauses and handlers with local state. Moreover, the paper includes more implementation details and a discussion about how our implementation ensures type safety. We have also provided the artifact for our paper, including all the Haskell source code and the benchmarks, which can also be found in the GitHub link. Finally, for the theoretic aspects of the evidence passing semantics, we encourage interested people to read our SFP paper or watch the talk for more details. That's all. Thank you for listening.